This is our Ruyer reading group, continuing our reading of Cybernetics and the Origin of Information. So we're still on the first chapter. We're picking up on page 29 of the translation, still in the first chapter. So he's like analyzing the different types of what he calls information machines. So of course, from our perspective in 2024, we think first of electronic computers. When he's writing in I guess the 50s and 60s, this is like, I mean, there were electronic computers, of course, but they were not, part of everyday life for like every single activity that we do as they are today. So there's like more, I guess, variety of information machines that he is talking about. So he mentioned like mechanical adding machines, which I think might still have been in use in like office settings at this time. So again, these are like machines that just have, sets of gears and so on that are like set up in such a way that you can enter a number on like a keypad, like a typewriter or something, and enter the operation, enter a second number, and then it will like display the results. It's like a purely mechanical process. There's just like the numbers are represented by gears or like notches on a gear or whatever, and the connections between these different gears are set up in such a way that it like performs the addition or multiplication or whatever correctly. So obviously this like set of gears has nothing resembling a human understanding of what a number is, what multiplication means, and so on. It's just pieces of metal that are shaped in a certain way. And then of course the electronic computers that he's talking about likewise have nothing resembling what we would call understanding, human understanding of a number or multiplication. It's just sets of transistors that are set up in such a way that the flow of electricity through the system also sort of produces something that a human can look at and say, yes, this is the correct answer to the calculation that I put into the system at the input. So Ruyer sort of insists on this, that like computation or these like information machines in general involves completely ignoring the meaning or understanding or whatever term we want to use for like a human grasp of an operation, and just sort of translates it into these like physical processes that are set up in such a way that the output of this process is interpretable by a human being as the solution to the problem or the result of the calculation or whatever. So like in the case of logic that he talks about, so there's of course the Boolean logic or Boolean algebra sort of translation, that you take any proposition and you can just translate it into a 1 if it's true and a 0 if it's false. And then you can combine simple propositions into complex ones using operators like and, or, if, then, etc. And then Boolean algebra gives you rules for calculating the truth value of the complex proposition from the truth values of the simple propositions that make it up. And again, this is like completely abstracting from anything about the meaning or significance or understanding what these sentences are supposed to signify. You just any true sentence, whether it's 2 + 2 = 4, Paris is the capital of France, whatever, some statement that is extremely important to your relationship with your partner or family or friends or whatever. Any of these propositions, they all just get translated into 1, and then any false proposition gets translated into 0. So like it's even like you could call it like simplistic, sort of like a reduction of anything that is important to anyone that like has ever existed. As long as it's true, it just gets translated to 0, or I guess translated to 1. Sorry. But what's interesting is that if you do these kinds of sort of very simplistic translations, you can actually get computers to perform, or information machines in general, to perform operations that sort of correspond to or simulate or whatever, that give us a result that that we can as humans interpret as the solution to a problem, or of course with our much more sophisticated computers today compared to what he was familiar with in the 50s and 60s. You can have computers that will translate a text, generate music, etc., etc. All these things that when a human does it, we think of them as sort of intellectual operations or cognitive operations. Computers can at least do something that is analogous. That the output is something that you can read the text and say, yes, this is a more or less decent translation of the original text, or this is actually a piece of music that you can listen to and that sort of makes sense, even if it's not like that good in terms of like artistic quality of the music. In general, you can like take what the information machine or the computer outputs and understand it as if it were sort of an intellectual product of a human being. And I guess the question that arises from that is like, given the fact that you can produce this that an information machine can produce this kind of output that is at least similar to the product of an intellectual operation that a human performs, is this similarity sort of is that a meaningful similarity, or is it just sort of like a sort of accident, I guess? Is it the case that what the computer is producing is the same kind of thing as what the human produces, only maybe not like as good or not as sophisticated or whatever? Or is it the case that the human composing a piece of music and the computer that generates it automatically are doing completely different things, that these are like different in kind, and it's just there's a sort of like superficial resemblance between the two outputs. And of course, Ruyer is going to insist on the second answer, that information machines and humans that understand and produce something meaningful, these are completely different types of operations. There's a difference in kind between them, and the fact that you can get computers to perform calculations that if a human did them would be considered intellectual operations is just it's just a sort of superficial resemblance, and it doesn't mean that the computer itself is doing something intellectual, or that conversely that the human who is doing the calculation is similar in like a fundamental way, or is the same kind of thing as the computing machine. So that's sort of like the core question of this book, or the core point of this book. But it's also, I think, interesting to mention that for Ruyer, unlike most other people, it's not just human, intellectual performances that he's talking about, that like, performing a calculation or composing a piece of music or whatever. But he thinks that all living beings are essentially different in principle from these kinds of mechanical operations. That the development of an embryo into a chicken, for example, is itself analogous. It should be compared more to the human, intellectual operation of composing a piece of music, rather than comparing it to, say, like a computer program that would like simulate the development of an embryo into a chick. So even if you have like a simulation running on your computer that sort of produces something that resembles the development of the embryo into the chick, then that is, for him, it is a sort of artificial simulation that is in principle different in kind, or has this like ontological difference to the actual development of the embryo into the chick. And I mean, he doesn't really get into it that much in this book, but he of course has this other book, Neo-Finalism, and another book as well, Psychobiology. So like he thinks that there's this sort of intrinsically like intrinsic connection between the psychological and the biological, in the sense that the development, the sort of functionalism, I guess, or functionality of living beings and organs and cells within living beings, this sort of functional nature, the fact that they are for something, that they like are directed towards something, this is analogous or has this like intrinsic connection to the nature of human understanding as directed towards a goal or to realizing a value or something along those lines, as opposed to this sort of mechanical process. And especially like at the time he was writing this is like around the same time as the structure of DNA was identified, and the sort of explosion of molecular biology. that developed from there, which of course treats living organisms as these like extremely complicated micro machines of molecules that are set up in this intricate way to produce proteins and so on. And so Ruyer doesn't deny that there are machines in living beings. There is molecular machinery within our cells that does produce proteins and so on. But he denies that this is sort of that this captures what it is to be a living being as such. Okay, so yeah, let's get into the text from the top of page 29.
I can read. So I have a slight cold, so apologies in advance for coughing and stuff to our many listeners on YouTube. Feedback and self-regulation. It was James Clerk Maxwell who, in 1868, made the first theoretical study of an industrial feedback system. He analyzed the operation of the ball regulator, which ensures a constant speed for the steam engine, despite the differences in load. It is essentially a pendulum attached to a steam inlet. If the machine runs too fast, the centrifugal force lifts the balls that, through intermediate connections, decrease the intake. If the machine, loaded or braked, slows down, the centrifugal force decreases, and the balls, falling by their own weight or under the action of a spring, increase the intake. The regulator, quote-unquote, informed by the speed of rotation, transmits the quote-unquote information to the machine, which decreases or increases its speed accordingly. The new speed, quote-unquote, informs the controller again, and so on. The regulator acts in the opposite direction to that of the machine's operation. It corrects its deviations and tends to minimize its oscillations. This kind of feedback is called negative feedback. The thermostat is of the same type. It regulates the temperature of the boiler. The same goes for the automatic piloting devices of aircraft. If the aircraft rolls, this informs the vertical gyroscope's artificial horizon, which operates the valve for controlling the fins and straightens the plane. If this adjustment is excessive, a second action begins, which minimizes the oscillation. The study of the various types of oscillations and negative feedback poses delicate mathematical and physical problems, which we do not need to enter into here. In positive feedback, the setup is inverted, and the device uses the information to avoid, rather than search for, a certain level of functioning or an object that it is able to quote-unquote perceive. The use of the words quote-unquote positive or quote-unquote negative seems rather unfortunate, but is explained because in positive feedback, the recurrent energy acts in the same way as the operation of the machine, which races or returns to zero, or runaway. In both cases, the operation is not the result of a single thrust a tergo. A cause A, the primary operation of the machine, produces an effect B. A cause capital A produces an effect capital B, and another effect lowercase b, proportional to uppercase B. The secondary effect small b is related to big A, on which it produces a recurrent action. More precisely, small b is automatically compared by the machine to an ideal, in quotes, small bi, inscribed in the device by the engineer or user, and it is the difference small bi minus b which produces a recurrent action on big A. As a result, big A becomes big A prime and produces the effect big B prime plus small b prime. Thus, the automaton is mechanically finalized. By means of trial and error, it seems to seek an ideal state. In any feedback, the recurring small bi minus small b to big A current can be called the quote-unquote informant of big A. For example, while conducting an artillery shot, an officer at the forward observation post telephones to the battery commander, quote, too long, unquote, or quote-unquote too short. A radar registering the image of the goal and the image of the shot each time can correct the pointing device just as well by small vi minus b to big A feedback. The recurrent flow is automatic information, which plays exactly the same role as the information given by a conscious observer. Should I just finish this because it's just one more page? Or do you all want to stop here?
No, yeah, you can finish the whole section.
We consider each link in the feedback cycle separately, we find pure causality, that is, thrusts a tergo. But as it is a cycle, what is behind each link is also in front of it. The guiding ideal combines with the thrusts a tergo, and a de facto finality seems to emerge from the mechanical causality. However, this cyclical nature on its own is not enough to characterize feedback. Information not contained in the machine structure must be introduced into the cycle. Indeed, it can be said that any operation of any machine is cyclical, since the machine can always return to its starting point. We speak of the cycle of an internal combustion engine or a steam engine, even without a regulator. But in an ordinary machine, the different parts are simply arranged to order each other in a specific way and at a specific time. If, for example, a cam mounted on the axle of a wheel lifts a lever arm each time it turns, it cannot be said that the cam, quote unquote, informs the lever without stretching the meaning of the word to the point of absurdity. The cam simply pushes the lever in a conventional way and in accord with the structure of the machine. In the combustion engine, the spark that produces the explosion that drives the engine, that controls the magneto, is produced by the magneto, and so on indefinitely. In a feedback machine, the recurrent flow of information also acts through a tergo thrust, but this time the information is not contained in the machine structure. The ball regulator undergoes a thrust, which the intake register also undergoes the thrust of the regulator. What is new here is that the thrust information given by the regulator is not inscribed in advance in the machine structure. It takes into account the various internal or external incidents that can change the engine's running speed. Therefore, we can now define a feedback machine as a cyclical functioning with a regulating loop through which a current of information flows automatically compared to an ideal, in quotes. In a machine without feedback, the conscious supervisor plays the role of the regulating loop. The supervisor observes the standardized functioning, compares it with the ideal to which he has the task of keeping, and intervenes to bring the standardized functioning closer to this ideal. In order to regulate, feedback performs these three functions. 1, it observes. 2, it compares. And 3, it intervenes. One must not confuse the progress made in the primary functioning cycle when an improvement in the structural arrangement of the machine makes it possible to do without the muscles of a worker with the progress made with the regulating loop. This loop, which was previously represented by a supervisor and is now performed by feedback, makes it possible to do without the brain of a supervisor. This description of feedback seems relatively straightforward to me, that even though, in non-feedback machines, you obviously have parts acting on parts, and these parts return to their starting positions. In machines with feedback, there's the same action of parts on parts, but then there's a programmed ideal and some kind of mechanism that can intervene in the functioning of the other parts, which compares the relation of the function between the parts to the ideal and then regulates it on that account.
Yeah, and I think there's also a key point here that the feedback operation involves bringing in information from outside of the machine in terms of the difference between the current state of the machine or of whatever the machine is doing and the ideal or the goal state that it's supposed to be achieving. So like this example of the governor in the steam engine. Now this is like a classic example in this is like almost the sort of like proto cybernetics paper is Maxwell's paper on the governor. And it's interesting also just as an aside to point out that this device was produced long before it was actually analyzed mathematically by Maxwell. So like you had technicians of some kind who like set up this governor system on a steam engine without having any sort of theory of feedback systems and so on. That was Maxwell identifies or sets up this theoretical analysis probably a few decades later, and then it's like almost 100 years later that feedback as a concept is sort of isolated and made into the core of this cybernetic theory. But yeah, so coming back to this governor process, so you have the steam engine that produces a certain output. You can use it to run a some kind of cotton mill or whatever. If we're looking at like 19th century factory hellholes. And then you want to ensure that the output of the steam engine is even, so that like if you have more machines linked up to it, more looms or whatever, it will output more power to keep all the machines running at an even rate. And then when you have fewer machines connected to it, it will reduce the power output so those machines don't like speed up and break down and so on. And of course, at one point in the sort of earlier development of these machines, you actually had a person. Often it was like a 6-year-old kid that would like operate like speed up and slow down the machine, according to like to keep it at the right rate, so that or sorry, speed up and slow down the rate of the steam engine, so that all of the looms or whatever that are attached to it are operating at the right rate. So of course, from the perspective of the owner of this machine, that means you have to pay this kid, obviously next to nothing, but at least enough that they won't starve to death too fast. And then someone comes up with the idea that maybe we can replace this kid who watches the looms to ensure that that they aren't running too fast or too slow, with like this device that would do it, that we don't have to pay. And so the way it operates is that you have like a sort of arm attached to the steam engine with a little ball or a weight or whatever at the end, and then as the steam engine speeds up, the arm and the arm has like a hinge on it. That's an important part. So it's like attached to the steam engine with like a hinge, and then as the steam engine speeds up, it means that the arm will rise higher. So the faster the steam engine goes, the higher the arm rises, and that allows more of the steam to escape, which tends to slow down the machine, or slow down the steam engine. So like when the engine is operating without a heavy load, it will speed up, the steam escapes, and then that will make it slow back down. And then when it's operating with a heavy load, it won't. The arms will be lower, less steam escapes, and more of the power is outputted to the looms or whatever that are attached to it, as opposed to just being sort of dispersed into the air. And so this allows you to replace the 6-year-old boy who's like watching the machine with this automatic device that you don't have to pay and doesn't get tired and make mistakes and so on. And what Ruyer points out here as like the sort of key difference between this kind of feedback operation and just like a regular cycle. So like in the steam engine, there's a cycle going on in like an internal combustion. Or sorry, it's not exactly an internal combustion engine, but there is a cycle going on in that you have like a piston moving up and down based on the steam pressure in the cylinder, and it's returning to its starting point and then repeating. So it has this sort of circular structure of the operation of the machine has this cyclical nature, but it's a sort of self-contained cycle in the sense that the steam engine will just keep operating in this cyclical pattern as long as you keep feeding fuel into it. It doesn't care what is happening outside that cylinder. Whereas once you attach this governor to it, then you have like an input of information coming from outside that determines what is the speed that the cylinder this engine is producing in the what speed of rotation is actually being outputted by this engine, and taking that information about the speed, the outcome of the operation of the engine, and using that to regulate the process itself. So it's that external information being inserted back into the operation of the cycle. This is what sort of defines it as a feedback operation, and not just like a cyclical machine that will just continue doing whatever it does indefinitely as long as it has the fuel or whatever resources it needs to operate. And the reason Ruyer is talking about this, as we like saw in the last week, is that he's analyzing or trying to understand the whole position of cybernetics, which sort of takes these feedback machines as being as like a model for explaining human understanding and goal-directed action. So when a person picks up a coffee cup and brings it to their mouth and drinks, this is for a cybernetician. This is essentially just a sequence of feedback operation movements. So you have this ideal state is like the coffee cup is at my lips and I'm drinking. This is like the goal that you're aiming towards, and then you have like some sort of measurement of the extent to which the observed situation is different from the goal of the coffee cup at my lips, and you act in such a way as to reduce that difference. So your arm brings the coffee cup closer to your lips until it actually touches your lips, and then the difference is zero, and then everything's good. This is the sort of, obviously that's a extreme oversimplification of the cybernetic position, but that's like the general sort of structure. Is that so the operation of a human being grasping a coffee cup and performing a voluntary action is essentially the same as the operation of the governor that keeps the steam engine functioning in the desired range of output. And of course, Ruyer is going to argue against this position, but he does think that cybernetics is sort of an important reference point or an important position to take account of. That it's not like completely misguided and irrelevant. It's like something we need to study and analyze, and that's really the whole point of this book. It's by sort of working through the reasons for why cybernetics is not capable of accounting for human goal-directed action, human understanding, and so on. It's through that process that we get a better grasp of what human understanding is. And so, it's a similar strategy to what we saw with Merleau-Ponty, where he's like analyzing these physiologists and psychologists trying to explain human behavior and animal behavior. And he, of course, disagrees with their attempts, especially the reflex theory, of course, but then also the Gestalt psychologists. He's going to criticize their positions, but he takes it that analyzing and criticizing their positions is an exercise that allows us to get a better grasp of what human understanding is and human behavior, and what human behavior is. So it's not the case that we just sort of reject these attempts to explain human behavior in terms of feedback or minimization of tension or whatever. We sort of carefully analyze, even at the level of like experimental design, what assumptions they're making and whether those assumptions are valid, how they interpret the results of their experiments, etc. So it's a much more careful and I guess respectful approach to these scientific theories, that we take them seriously and analyze the extent to which they're successful, as opposed to just sort of rejecting them altogether. Yeah, so Angus' comment here is about, this is sort of like a typical French way of doing things. And so I think sometimes it can be a little bit frustrating when you have to read like a 200-page book to like that goes through like a dozen different experiments in like sometimes excruciating detail, to sort of figure out what exactly is the point. Like why do I care about this rat navigating a maze experiment from 100 years ago, as opposed to if you have like a analytic philosophy of science paper, it'll just like state, here's my position at the outset, and that is sometimes a little bit easier to work with. But it's also, I think it's sometimes having the patience to go through that 200-page book or whatever, and look at all these experiments and try to decipher what are the assumptions that they're making that they don't even necessarily realize they're making, and are there other assumptions we could make, like could we set things up in a different way and understand the results of this experiment in a different way. It's less sort of straightforward to figure out what's going on, but sometimes more rewarding. You get like a better I don't want to use the word deeper because that's kind of like a cliche, but like you get a more thorough understanding of why you would want to make a certain assumption or not, based on this like very detailed analysis of what the what the consequences are of making that assumption, and what types of experiments will follow from making that assumption, and what type of interpretation of the results of the experiments, and it can sort of lead you to want to try to do different things, to interpret results in different ways, and potentially do different kinds of experiments that would sort of implement different assumptions. I think like when we were reading the Merleau-Ponty book, there were passages where he would like spend 5 or 10 pages just like talking about like 2 or 3 experiments, related experiments or whatever, and sort of analyzing in great detail what was going on. And sometimes you can sort of get lost in like the details of these experiments, and it's hard to grasp what exactly is the point. Like why are we looking at this in such detail? So yeah, you have to be able to like zoom in and out as you're reading. That like you sort of look at the details of this experiment, but you have like the bigger frame in mind at the same time. Like you sort of keep in mind why these details are important in light of the broader questions about the nature of animal behavior and human behavior and understanding and so on.
Yeah, speaking for myself, I definitely had to go back and reread a few of those descriptions of the experiments in structure of behavior. Like I remember rereading the description of that. There was the one experiment where there was a like yellow light, a lamp with yellow light, being shown on like a white wall, and window with daylight coming in, and the experimental setup was such that none of the perceived colors were the objective colors. Like the daylight appeared blue and the yellow light appeared white. It took me a long time to understand exactly. It's just hard without like a diagram or anything like that to figure out exactly how the experiment was set up. But then, yeah, I reading this experiment and others in detail, and then going back and trying to get a better sense of the philosophical argument that Merleau-Ponty was making. I think it makes the philosophical argument very forceful in a way that I don't find as much when I'm reading somebody like Deleuze, for instance, where if he's talking about philosophy of science, he's usually talking about like Bergson or Simondon's philosophy of science. So it's kind of a secondhand interpretation.
Yeah, I mean, Deleuze is always like reading, like even when he's doing philosophy of science or philosophy of mathematics or whatever, he does it through someone else's work. Like he's always, um, yeah, sort of, he's doing philosophy of science, but he's also doing philosophy of Bergson's philosophy of science, if that makes sense. So it's like a sort of second order analysis. Whereas, Merleau-Ponty is reading, the original text from these physiologists and psychologists, and going through in great detail like how exactly this experiment was set up, how they interpreted the results, and whether that is like the only possible interpretation, or whether there's alternative ways of understanding what was going on. And it does as Bats mentioned here in the chat, that some of these things, like even if you don't remember necessarily all the like arguments in the text that accompany them, you sort of remember these experiments that he described. The ape in the cage that stacks the boxes to try to reach the banana, and using the branch to reach outside the cage. And how it depends on what orientation of the branch, like whether it's set up in a certain way that the the ape can just sort of see, oh, this branch is like a arm lengthener thing that I can use, whereas if it's in a different orientation, the ape just doesn't see that. So some of these experiments, even if you like forget like what exactly the lesson that we're supposed to draw from them was, you still sort of remember this experiment, that you have this like image of this poor ape in a cage trying to reach a banana. um, um, and that sort of sticks in your head, and then you can just sort of like almost reconstruct the argument in the book just by thinking about that experiment again. Um, it's a different approach than I think what we are more familiar with in like more contemporary philosophy of science. But maybe it would be good to bring that back into circulation again. Yeah, just a sort of aside. Yeah, so Bats has mentioned how like when you remember the experiment but not the argument, then it sort of forces you to think it through for yourself again. That you have to like sort of reconstruct it in your head rather than just like remembering the argument yourself. And this sort of reminds me of a completely different like intellectual context. But Fichte has this sometimes very frustrating habit of changing his whole terminology from one text to the next. That um, and then he justifies it by saying that he doesn't want people to like memorize formulas of like Fichtean philosophy, like this is what the sort of slogan of Fichte is. He wants people to think things through for themselves and sort of perform the operations and intellectual operations themselves, as opposed to just copying these formulas. So yeah, it's a similar kind of thing here, where you might only remember from Merleau-Ponty's book the experiments that he describes, as opposed to how he interprets them and the arguments related to them. But as long as you remember those experiments and sort of the general vibe of the book, then you can like sort of reconstruct it for yourself and think it through for yourself. Yeah, sorry, was popping something into the chat here. Right, so yeah, we can go on to the next section. Bats, would you like to read from organic feedback?
Yeah, sure. Okay. Organic feedback. The living organism is full of such self-regulations, and physiologists very quickly adopted the notion of feedback that industrial technology offered. The living organism is full of such self-regulations, and physiologists very quickly adopted the notion of feedback that industrial technology offered them. This was generally in the hope of giving a mechanical explanation of the actual finalization of organisms. For a long time, moreover, these feedback systems had been defined under other names. Herman J. Jordan used the term quote-unquote amboception to emphasize the difference between an isolated causal action and the connected quote-unquote multicausality or quote-unquote causal framework. An apple falls from an apple tree and kills a mouse that was there, a causal action. A stone is supported by 3 pieces of wood. Between these 3 pieces of wood is a piece of bait. A mouse gnaws at the bait, the stone falls and kills the mouse. In the trap, there is a quote-unquote causal framework and quote-unquote amboception. The bait is held on one side by the pieces of wood and on the other by the mouse. In the organism, the secretin of the duodenum, for example, acts as an amboceptor, quote-unquote, between the acidity of gastric juice that, passing through an intestine or the intestine, would prevent intestinal digestion, and pancreatic juice, which neutralizes gastric acidity. We know that the equilibria in the body are, in general, not static, but homeostatic. They remain stable despite variable external conditions. If the organic balance were static, and simply measure the resulting average of internal and external forces, life would be very precarious. In fact, organic equilibrium is generally not a result. It fully maintains a certain optimum value. Our blood maintains exactly the same acidity, even if we drink vinegar. It doesn't become more fluid, even if we have just absorbed a liter of water. Homeotherms keep the same constant temperature at the equator of the polar region. All homeostatic processes represent feedback, generally operated by slow-acting systems, such as the sympathetic and parasympathetic nervous systems, glands and smooth muscles, chemical messengers and buffer solutions. Voluntary acts, on the other hand, represent rapid feedback involving striated muscles and circuits of the central nervous system. Gestalt theory, of which we have emphasized the similarity to cybernetics, and will do so again more than once, has described this feedback under the name of quote-unquote circular processes. I am in the dark, and a light appearing on the periphery of my visual field makes me turn my head and eyes, then incites me to walk towards it. The functioning of my oculogyric and cephalogic centers, and then my locomotor muscles, is dynamically controlled by the result already obtained, and by the residual tension between this result and the goal. The Gestaltists reject the explanations according to the preformed nervous arcs, which they think would imply an improbably large number of prepared assemblies. Montage. Cortical centers are not sets of isolated and juxtaposed pathways. They are quote-unquote free dynamic interactions, there are quote-unquote free dynamic interactions between all these pathways, similar to those of a magnetic field between the spirals of an induction coil. Cortical centers act in their unity, like fields of forces that re-equilibrate on their own. The final command to the effectors depends each time on this re-equilibration and can be improvised in detail. As long as I am not near the light, my field of behavior is still out of equilibrium, and any movement of approach by any mode of locomotion that improves equilibrium would be favored. The quote-unquote circular process, while very similar to feedback, does not have a specialized conductor. The information is not brought back to the entry of the system by specific recurrent fibers. It is entirely one with the dynamism of the field of behavior. Cybernetics, in its orthodox form, reverts to the more classical theory of nervous circulation as subservient to conductors. If I want to take a full glass on the table, the pyramidal cells of the motor zone must be able to send impulses to the muscles of my arm. But it is not enough that I am not paralyzed and that I have good effectors. The central nervous system must be informed at each instant of the effect already obtained by the first impulse, and this information must be combined with that from the other sensory organs, so that subsequent impulses correctly complete the action. If the recurrent circuits of information were damaged, my movements would be clumsy and conventional, like walking in cases of tabes dorsalis, where there is no paralysis, but the recurrent information is lacking. The recent discoveries of physiologists, especially those of Laurent Denot, seem to confirm the theory of orthodox cyberneticians against the Gestalt thesis. There are in fact recurrent fibers of information coupled with fibers of affection. The feedback arrangement of the conductors allows us to avoid the difficulty emphasized by the Gestaltists. For any theory appealing to quote-unquote assemblies and quote-unquote rails, theoretically, a single reflex arc, provided it is controlled by a regular impulse, can perform different actions, depending on the information received. Gray Walter's artificial animals move toward the light wherever it appears, without having the multitude of conductors that Kafka considers necessary in the hypothesis of nervous paths serving as rails. Nor does the DCA canon with automatic aim have any such quote-unquote rails. A motorist can drive a car correctly, almost without error, with steering that is more augmented than what he is used to. This is because it is guided by the result achieved and not by a one-way motor habit. In fact, an automobile driver is unable to say, even very approximately, by what angle he should turn the steering wheel of his familiar car to take an intersecting road on his right. This is a striking indication of the completely improvised nature of the movements of affection. An animal that is mutilated after having been taught to leave a labyrinth so as to prohibit some of the learned movements, improvises compensating movements and arrives at the result in another way, provided that some of the recurrent circuits are intact. However, there is not much difference between the circular process of Gestaltists and the feedback conductors of cyberneticians. Feedback is, after all, only a circular process, quote-unquote, on rails, a channeled dynamism. The Sperry gyro of the automatic pilot perfectly meets the requirements of the circular process, as well as those of the feedback. The two schemas have this essential feature in common. They explain finalist regulations, quote-unquote, molar behaviors, as predictable according to their aim, independently of the detail of quote-unquote molecular functions, without appealing to anything more than efficient causality. One can say of both the feedback systems and the circular process system that they can be automatic and finalized at the same time. Both cyberneticians and Gestalt theory stand in absolute opposition to the interpretations of introspective psychology. The latter see in the de facto purpose of behaviors the manifestations of a transcendent principle, which is irreducible to explanations or assemblies according to physical, mechanical, or dynamic laws. Clark Al Hull, among others, has stated with particular clarity, for the use of psychologists, what could be called the principle of the possible robot. Nothing should be assumed to happen in an organism that cannot also happen in a fully automatic robot. Oh, and it ends there.
Right, thanks. Yeah, so a couple things. So I mentioned in the chat here when he talks about homeostasis in living beings. So the way that in homeotherms, or what we know as warm-blooded organisms like humans, temperature is kept stable. So yeah, I mentioned in the chat that this is slightly inaccurate because like in the case of temperature, for example, our body temperature is not 100% stable at a precise temperature. It actually fluctuates around a temperature. So over the course of a day, for example, your body temperature changes in alignment with menstrual cycle. It changes as well, et cetera. And of course, when you're exercising, your body temperature will increase. And then for example, he talked about the blood, that if you drink a lot of water, your blood doesn't become watery. That's not, again, entirely true. So for example, when someone comes into the hospital with dehydration, they'll hook you up to an IV to get fluids into you, but the IV is not pure water. It's a saline solution, because if they just sort of pumped water into your bloodstream, then your blood would actually get watery like that. And so the saline solution is sort of matches the composition of your blood, or it ensures that the saline level in your blood doesn't change as you sort of take in more fluids. Because if you just sort of pumped water into people's bloodstream, the saline level in the cells would be much higher than outside the cells, and bad things would happen as a consequence. I think if I remember correctly, it would the cells would start taking in water. The water would flow across the cell membrane, and that would eventually make the cells burst. So that's obviously not good. So the point is that these homeostatic mechanisms or processes in living beings, they don't sort of keep the value that they're stabilizing fixed at one value. There's a certain range, and those ranges fluctuate sometimes in relation to what the organism is doing or experiencing, and also sometimes on these cyclical patterns, daily or monthly or whatever. And then also they are only effective within a certain domain. So if you drink a liter of water, your blood will keep the same composition, but if you drink 20 liters of water, somehow that might actually affect that might actually water down your blood. Although I think you would probably just vomit first. And that again is a sort of homeostatic mechanism, that you vomit up the water rather than just keep ingesting it and affecting the composition of your blood. But yeah, so the point of talking about these homeostatic mechanisms here is that these are quite it's quite tempting to interpret them as analogous to the kinds of feedback mechanisms like the governor that sort of inspired cybernetics. That the homeostatic process that keeps our body temperature within a certain range is essentially the same kind of thing as the thermostat in your house that keeps your room temperature within a certain range. And Ruyer doesn't deny that. He doesn't say that it's completely false that these are the same kind of thing, but he thinks that he doesn't get into it that much in this book, but so he says, yes, there are machines in the human body. There is something like a feedback machine that keeps our body temperature in a range, and it's essentially the same kind of thing as a thermostat. But the development of the human body that results in the creation of this machine is not itself mechanical, is not itself explicable in terms of machines. And so the key difference that he wants to emphasize is that the thermostat is built by a human, that a person has an idea or a diagram or whatever that tells them what to do. They sort of keep this idea or this goal state in mind, and they put together the different components, or maybe build the components themselves or whatever. Anyway, they implement this idea in some kind of electronic or mechanical device. They produce this machine, but the machine does not produce itself. Whereas in the case of living beings, there are machines, similar to the thermostat in their body, biological machines, of course. But those biological machines do produce themselves. That the adult organism is produces itself from the embryo. It doesn't. There's no sort of outside force or outside entity that has the blueprint of the adult organism in mind, and then sort of puts the component cells and tissues together in the right way. It's actually sort of internal or intrinsic to the organism itself to build those machines within itself. So he takes this to be like an in principle or like ontological difference between these two types of entities, even if the outcome in certain respects is similar. That you have these biological machines that are analogous to electronic or mechanical machines, but the genesis of the biological machines is completely different than that of the artificial machines that we produce to generate the same kinds of effects. Oh, and also just one point of clarification that I put in the chat here, I should mention for those listening. He mentions here the DCA canon. So DCA, well, it's actually DCA. It's Défense contre avion. It's an anti-aircraft gun, is what he's talking about. So this is, again, one of the sort of origin points of cybernetics. Norbert Wiener worked on anti-aircraft guns during World War II. I guess there was probably a similar French program, or maybe the French, adopted the gun from the Americans. I'm not sure. Anyway, so these anti-aircraft guns, one of the sort of problems that arose in World War II was that you have planes that are now flying fast enough that a human operator of an anti-aircraft gun finds it difficult to target the gun at the plane, because if you aim at where the plane is, then by the time the shell or projectile, whatever, reaches that location, the plane has already moved to a different place. So you have to actually target where the plane is going to be and not where it currently is. And to some extent, you can just sort of, and this happens even in hunting birds, for example, that like as a shooter, as a hunter shooting a bird, you have to shoot where the bird is going to be and not where the bird currently is. But of course, birds fly much slower than an airplane or World War II era airplane even. And so like you can, learn to lead the bird much more easily than you can learn to lead the airplane. And so during World War II, they developed these sort of automatic targeting mechanisms that would allow, or would help the operator target where the plane is going to be as opposed to where it is. And so this involves sort of using these kinds of feedback mechanisms to like pinpoint the location better than the human operator could do alone. So that's what that bit is. And so like you have to so this involves a kind of substitution of the mechanical or electronic, I think it was mechanical at that point, device for the human sort of capacity to extrapolate a trajectory. So that a human watching the plane can sort of figure out where it's going to go, but that figuring out operation is too slow to effectively see the plane, figure out where it's going to go, and then target the gun in the right location. By the time the human has done that, the plane has already moved somewhere else. And so this mechanical process of extrapolating the trajectory helps to speed up the process and ensure that the targeting can actually be done fast enough to be effective. So it's sort of replacing what in a human would be this cognitive, at least maybe intellectual operation of figuring out where the plane is going to be. Replace that by this mechanical operation or electronic operation that performs the same kind of that gives the same output in this automatic process.
It's interesting to me that he argues that the cyberneticians and the gestaltists kind of end up in the same place. Just as a general comment, it's been cool to see, over the course of the readings we've done in this group, just how important Gestalt psychology was for all of these thinkers, and how different the conclusions that they draw from the experiments of Gestalt psychology can be. I don't know. Maybe I don't know. I guess it's hard to say if Merleau-Ponty would agree with this. Obviously he wasn't concerned to compare cybernetics and Gestaltism. He was also obviously critical of some of the interpretations and philosophical assumptions of the Gestaltists. I guess for Ruyer, you have, even though the Gestaltists reject the reflex arc theory, you end up with a similar kind of input and output system of some kind, which he seems to be saying for the Gestalt psychologists has this. I can't remember what word he uses. Specialized conductor, maybe, which kind of intervenes between the afferent and efferent aspects, which is similar, he's arguing, to the feedback mechanism or feedback conductor, like the governor.
Yeah, I think for Ruyer, I think the only difference between the Gestalt psychology and like the cybernetic approach to these kinds of problems is that for cyberneticians there are like these preset or preformed homeostatic processes. So things like maintaining temperature of the body, maintaining the composition of the blood, and so on. So he uses the term here on rails. So it's like almost that, like, you can picture like a mechanism that has like it's like the gears can only move in this like set of rails or whatever it is. Obviously, in the case of the composition of the blood, there are no like tiny gears or rails inside our bloodstream that are ensuring that the composition stays within a range. But like at the sort of schematic level, it's the same idea that like this process can only proceed in this like fixed way that will result in keeping the composition of the blood relatively stable. Whereas in the case of the Gestalt psychologists, they sort of deny that there are these fixed rails, or at least in the types of processes they're interested in, they deny that there are these fixed rails. So like visual perception, for example, that involves like finding the triangle or the the good shape among all the other lines that are partly obscuring it. This is like a standard CAPTCHA task now, with with letters instead of like triangles. But so machines are still not quite as good at humans at this task. Yeah, so this task of finding the good form is understood as a kind of minimization of tension, that like as long as you haven't found the good form, there's this tension or this like disequilibrium, and the process of identifying that good form is a reduction of tension. And this is sort of analogous to the reduction of difference between the goal state and the current state that is characteristic of feedback. And so like he talks about this. I don't know the exact example he's talking about with like the light. He doesn't go into detail here, but like as far as I can tell, he's talking about like you're in a dark room and there's a light somewhere, and you move in such a way as to go towards the light or to stand next to the light. And the idea here, there's a kind of like behavioral field of the observed world around you that has this tension, in the sense that there's like an attracting point, this light, and you are distant from this attracting point, and the distance between you and the light is a kind of source of tension, and as you approach the light, the tension reduces. And for the Gestalt psychologist, that doesn't mean that there's like this sort of preset mechanism in your brain that like sort of orients you towards the light. That may be the case for like these moths that like fly into a candle flame because they're attracted to the light. But for humans, of course, we can operate in this more flexible manner. We can, if we have a reason to do so, we can decide to move away from the light, for example, as opposed to toward it. And if there's like an obstacle between me and the light, I can temporarily move away from the light to get around the obstacle, and then return to the path that leads towards the light. Whereas we saw with the toad example that Merleau-Ponty talks about, where it just keeps trying to grasp the worm, even though it keeps hitting the piece of glass in between. In this case, the toad is not capable of taking this detour. So for the Gestaltist, there's no sort of preset mechanism that sort of leads the human to, orient towards the light and reduce the distance between itself and the light. But at the same time, there's this like field of potentials that like certain directions have this gradient of reducing tension, and others have a gradient of increasing tension, or at least not minimizing tension. And the behavior of the human will proceed down the path of this reducing the tension. So it's still sort of a mechanism. It's just not a sort of mechanism on rails, in a sense that it's not the actual like step-by-step operation is not preset, but the operation of the reduction of tension, the fact that the behavior of the organism will go in a certain direction is still the same kind of operation as the ones that are on rails, like the composition, preserving the stability of the composition of blood, for example. So like even though there are differences and they might be important in certain respects, from the perspective of like the kind of explanation that is involved for Ruyer, these are like the differences are not relevant here. That it's still understanding goal-directed behavior as involving this kind of reduction of tension or reduction of difference, or this sort of circular comparison operation. It's maybe also worth mentioning here as like maybe a more sort of contemporary connection with this is that the majority of AI systems today use some variation on a neural network architecture, which involves an algorithm known as gradient descent, or a set of algorithms called gradient descent, which involves precisely this kind of minimization operation that you have like, to give like a very schematic like explanation of it, you have like some sort of like you start off with a set of units that they're described as neurons, but they don't really resemble actual biological neurons very much. But you have these units and you have weights that indicate how strong the connection is from one to another. And you start off with just randomly assigned weights, and you sort of feed in the inputs and get it to produce some output. And of course, at the beginning, it doesn't. There's no like value or like pattern in the outputs. It doesn't really correspond to the inputs at all. But the training process of this system or this model will involve adjusting the weights in such a way as to reduce the error. So this is in the case of supervised learning. So you have like a set of labeled outputs. You have like pictures that you tell the machine this is a dog, and you get the model to predict a bunch of other pictures and figure out to give an output that says yes, this is a dog, or no, this is not a dog. And the first stage, it will be completely arbitrary. It will just assign the label dog or not dog like randomly to pictures, and then you sort of feed in the errors that you said picture 1 was a dog, but it's not. You said picture 2 was not a dog, but it is, etc. And then you feed those errors back into the weights of the model, and it uses this gradient descent algorithm to adjust the weights in a way that reduces the errors. And you keep doing that over and over again until you finally get the weights adjusted to the point where it predicts, or that it assigns the label dog to the picture with whatever the desired degree of accuracy is. So yeah, these like AI systems obviously are quite different in their design than like the kinds of computers that he was talking about, but this error minimization process is still sort of the core of how these machine learning systems work today. Okay, so I can read the next bit. I think we're on 34 at interested sensitivity and perception. Is that right? Right. Okay. Interested sensitivity and perception. The quote unquote interested sensitivity of a thermostat concerns the temperature. Its organ of quote unquote perception is a simple thermometer. The watt regulator is speed sensitive and quote unquote feels the centrifugal force. We are not very impressed by these metaphors because in these devices there is no staging, mise en scène, that can remind us of the way a living being stages the perception of an external object. If the information is provided to the automaton by a photoelectric cell, and if the automaton is equipped by its manufacturer with phototropism, the effect is much more surprising. Gray-Walter's artificial tortoise, a three-wheeled device powered by electric motors and batteries, is topped by a photoelectric cell that controls the motors by relay to direct the automaton into the light. Moreover, the tortoise is endowed with a quote-unquote stimulus, tactisme, kind of a strange translation. I'll have to look at that again. Anyway, tactisme. When the shell hits an obstacle, a circuit closes, which neutralizes the phototropism and releases the steered wheel for a moment. The device then seems to grope, scalloping around the obstacle before resuming its path toward the light. The photoelectric cell is also sensitive to the brightness of light. If the light source is too bright, it acts as an obstacle and the tortoise avoids it. But when its battery has been sufficiently drained, the bright light no longer activates the quote-unquote obstacle effect, and the tortoise moves toward it. If a bright light shines on a battery charging device, the tortoise seems to go after the electrical food until the photoelectric cell can again act to move it away from the bright light. The automaton thus seems to imitate both the internal and external sensitivity of living beings and what Edward C. Tolman calls psycho-organic, quote, variable demands, unquote, such as hunger. Despite their quite spectacular character, Gray-Walter's quote-unquote animals are rather crude devices. Their reactions have a quote-unquote all-or-nothing character despite the twofold sensitivity of the cell. The perceived object, light, or obstacle is only a trigger. It has none of the characteristics of a signal or sign acting by its form, that is, literally providing information. Most industrial servo mechanisms that use the sensitive quote-unquote perception of photoelectric cells are of the same order. They can be used to protect an installation, the device triggering an alert apparatus when someone approaches a capacitance plate or breaks an infrared beam. Or, and this is already something of a higher order, to automatically control delicate or dangerous practical work and to guide the work of a machine according to a template whose form is examined step by step by the cell. Even in this last remarkable case, where the machine seems capable of seeing a form, it is clear that it does not perceive, that it does not quote-unquote recognize the form as a form, since it limits itself to following the contour step by step. Cyberneticians very quickly grasp the importance of the problem of the perception and recognition of forms as universals, that is, as overall schemas that psychophysiologically preserve their identity despite the different transformations of their geometric appearance in the narrow sense of the word. We recognize a familiar object whether we see it from afar or up close, from the front or from the side. We recognize a circle as a circle and a plate as circular, whether it is near or far, and therefore whether it projects a large or small circle on the retina. We recognize it whether it is seen from the front, side, or at a three-quarter angle, that is, whether it projects a circle, an ellipse, or an elongated trapezium on the retina. According to the assumptions of cybernetics, this performance must be done by nervous assemblies and it must be imitable by mechanical assemblies. The reading machine of Pitts and McCulloch, to which we have already alluded, carries out, using appropriate relays, an independent scanning of the dimension of the letters to be perceived. But it is much more difficult to imagine a machine that would be capable of recognizing a plate, whether it is seen from the front, the side, or on a three-quarter angle. In short, this would be a machine that would work on similarity and that would be able, to use the words by which Kant defines the role of the schema, and that W. Russell Brain takes up again, to subsume, quote, subsume an object under a concept. Gray-Walter's tortoise heads for its quote-unquote hutch when its battery is flat, because this hutch is mounted with a bright light, which triggers the power unit. But it does not recognize the form of its hutch from any perspective. If we can stop here because there's like another couple pages in this section. I just want to recognize how incredible it is that there's a neuroscientist in the early 20th century whose name is Brain. I don't know. It's like he was destined from birth to have that job, I guess. And there's another one I think he mentions a little bit later named Head, which is also pretty cool. Anyway, so yeah, this is like a more interesting example. This homeostat, this artificial tortoise. So it's more than just so the thermostat is just sort of responding to this one stimulus or this one input, the temperature, and it either turns on the furnace or turns it off. That it's like extremely simple operation. But this artificial tortoise has a couple different feedback mechanisms that interact with each other, and the result is, it's still a very simple sort of process, but it's a lot closer to what we would recognize an animal as doing. So something like hunger. So it's sensitive to the level of charge in its battery, and that gives it sort of a variable response to the brightness of the light. So when the battery is highly charged, when it has a like a nearly full battery, it will avoid lights that are too bright. But then as its battery gets decharged, and it's at a lower level, the light that it would have avoided earlier is now it's now attracted to. And so you can compare this to like an animal that maybe has certain food preferences, that it prefers food source A to food source B. So when it's relatively full, it will avoid B and go for A instead, or keep searching until it finds A. But then as it gets hungrier, it sort of makes do with B, even though it would prefer A. So this is like maybe a similar operation, or you can think of say the food source is also in a location that is near a predator, and when the animal is not hungry or is relatively full, it will avoid that food source because the predator is nearby. But then as it gets hungrier and hungrier, it will be more likely to approach the food source despite the danger of the predator. So here, this device, and then so the other sort of element of this device that is interesting is that it combines. So it has this photo cell that is sensitive to light, but it also has I'll have to check that translation later. But this sort of tactile sensor, so that when it runs into something, so it's like directed towards the light. It doesn't have any sort of capacity to determine that there's an obstacle between it and the light, but it runs into this obstacle, and then this tactile sensor detects that it has run into the obstacle, and that sort of disconnects the steering mechanism from the photocell temporarily, which makes it just sort of randomly search, or search in quotes. It just sort of randomly moves around until it finally gets past the obstacle, and then the photocell re-engages the steering. And so this in some ways resembles, like, you can picture, I don't know, a worm or something that is moving in a direction, like following a gradient of, like, there's good stuff in this direction, there's food that it can smell or whatever, and then it runs into an obstacle of some kind. It doesn't know, like, the shape or the nature of this obstacle, but it just sort of randomly moves around until it finds the edge that it can go around, and then get past the obstacle and keep going in the direction of the food. So this is maybe a similar response of this animat or homeostat device to. It's similar to this, like, simple animal behavior of just sort of randomly searching until it's capable of proceeding towards the goal state again. But what Ruyer points out is that this machine is not doing something. It's not doing anything that it resembles, like, a human or even other animals grasping a form. So, like, he talks about recognizing a circle, or recognizing a circular plate, for example, despite the difference of orientation of the plate. So when you look at a plate from an angle, it's not like being held directly parallel to your retina. The image projected on the retina is not a circle; it's some kind of ellipse. But we still, like, you still look at the plate; it looks circular. It doesn't look like an ellipse that suddenly becomes a circle as you rotate the angle of the plate. And this is, Merleau-Ponty had talked about this, I think, exact example of the shape constancy, that we don't see objects as changing shape as we move around or move the objects, and the angle between the object and our eye changes. And again, this is also like a standard CAPTCHA task. You have, like, labeled the images that contain a bus, for example, and there's some that are far away, some that are close, different angles, weird, like, grainy image quality, etc. But you can still recognize that it's a bus. Whereas, and the reason why this is a CAPTCHA task is that it's difficult for artificial systems even now to recognize the bus in all these different orientations and distances and so on. And obviously the capacity of electronic computers to do these tasks has gotten like astronomically better in the time between when Ruyer was writing and now. So like he mentioned this like letter recognizing system that Pitts and McCulloch had put together. And optical character recognition is now pretty good. That you can take a photo on your phone of a page from a book, and you can have it pick out what the letters are and copy the text. And this is like pretty simple to do now, but it's relatively recent, like in the last 20 years, that this has really gotten good. But yeah, so it was a non-trivial task to get computers to be able to do this. And so for things that are like more complicated than letters, and even like I mentioned, the CAPTCHA task involving letters with like weird lines through them, and the letters are at different angles. This is a CAPTCHA task precisely because computers are still not that good at doing it. So like humans are still better at recognizing letters when they're in these strange orientations and have like and they're partly obscured and so on. Better than computers are capable of doing that.
Yeah, thank you. The point about CAPTCHA's the CAPTCHA images is helpful. I was trying to think when I was reading through this whether Ruyer's analysis would change. Because as you mentioned, machine vision has become a lot more is much better developed and more complex and works a lot better than it did when Ruyer was writing this. What I was also thinking is the difference between the way a machine learns to recognize an object being fed this massive data set of images in order to kind of get better at like recognizing a dog in like bright light versus fainter light, and the obvious difference between that and like a human child who obviously once they're old enough to kind of recognize objects in general, doesn't really get confused about what they're looking at if they're like looking down at the dog from sitting on a chair versus like standing on the floor kind of at like the same height as the dog. But I don't know if that really how that fits into his argument here with the point about the schematism, and as he will talk about, as he'll mention briefly, the basically geometric transformations posited as the mechanism underlying this schematic capacity that human beings have, of which he will be critical in a slightly different way.
Yeah, it's interesting that you mentioned the dog example, and I had mentioned that about like the training an AI system in photos as well. But it's interesting because when Kant is explaining the concept of the schema, he actually uses that exact example. He says like, so we have like a concept of a dog, an animal with certain properties, quadrupedal, barks, etc. But then, of course, if you just have this concept of a dog, it's just this sort of static list of properties. It doesn't really help you determine whether you are actually whether this thing in front of me is a dog or not. You have to find a way of like applying this concept to your experiences your perceptual input that you're receiving now. And so his sort of term for this mediation between this concept, this abstract concept, or this list of properties, and the sensory input that you're receiving is the schema. And so like your capacity to apply the concept dog to certain sensory inputs and not others in a more or less accurate way is a schema. And he, this is like, a pretty obscure element in the first critique. Yeah, this mysterious faculty, or I forget exactly the word he uses. And, Heidegger, of course, will sort of tie this in with the imagination. And I think, he's obviously drawing from things that Kant says, but it's, again, very, very obscure, and it's like only dealt with in this one little passage in the first critique. But the schema has something to do with time for Kant, that like schematization of a concept is like an application of the concept to some sort of temporal flow of sensory input. And so this involves, like in the case of the dog, you don't just get like a sort of static snapshot of like some pattern of retinal stimulation at a certain time. You get this sort of flow of retinal stimulations across time that is dog-like in some sense. That like your capacity to recognize a dog is not just a capacity to, like in the case of these AI systems that are trained to recognize dog images, they are just given these static snapshots of a photo that is labeled dog or not dog. Whereas a human, like in the case of the child, like you mentioned, this child that sees a dog will see the dog from a variety of angles as the child moves around, as the dog moves around, etc. And we'll see this like continuous flow of dog shape, happening in relation to their eyes. So like when you have this, so at one moment you have this dog-shaped image, you sort of, if this dog-shaped image suddenly like seemed to, was replaced by, I don't know, an apple-shaped image, you would obviously be very confused and would not think, oh, there's a dog here. So like your capacity to grasp that this, set of experiences or this flow of experiences is a dog is related to the way that this flow of experiences changes in a certain way in that, the dog might move or change its orientation towards you or whatever, but not in other ways, that the dog won't, turn into an apple all of a sudden or like disappear. So like this temporal structure of experience is sort of how, or is tied up with in some obscure way, our capacity to apply these abstract concepts to our experiences. And yeah, so as Angus points out in the chat here, and he sees where I'm going with this. So this is connected with like this melodic aspect of consciousness that we saw with Merleau-Ponty, and as Ruyer is emphasizing as well, that like when you grasp something as a dog, you're not just like grasping the static snapshot that you are of retinal stimulations that are happening at a certain instant. You are grasping like the structure of the flow of visual experiences that passes through the moment that you're at. That like there are certain like the past was dog-like, and that dog-likeness is proceeding through the present, and you have this like anticipation in Husserl's sense. You have this anticipation that or protension, I think is his word, that the dog-likeness will continue into the future. It won't just suddenly turn into an apple. And so this like melodic grasp of the whole temporal structure of the dog pattern is involved in the human capacity to recognize this object or entity in front of me as a dog. Whereas in the case of these machines or machine vision systems, it involves again just this sort of static labeling of a snapshot as dog or not dog. But it's also probably worth mentioning, this is not like maybe quite as firm of a distinction as it was in Ruyer's time, because now we have, of course, computer vision systems that don't just the ones we're more familiar with are the ones that are analyzing static photos, but there are of course video analysis systems as well. They're like not as good and they're more complicated to use, etc. But this is something that a lot of sort of intelligence and police agencies use. Like there's like gait analysis systems where like you can take a video of a person walking and analyze the way that that person walks, the movement of the person's body to try to identify who that person is, which is pretty creepy. Or like watch a video to pick out the faces in the crowd and then try to match those faces to like a database of photos of faces. So yeah, again, it's not quite the same thing as the child that learns this dog schema, but it's more of a, like the gait analysis example in particular is more of a approximation, I guess, to this temporal structure compared to just looking at a photo of a face.
Do you know, or does anybody know whether the the AI like video production programs I assume that they're also trained on video. It's interesting. If so, it's interesting in that respect that, like I've seen these videos circulating on Twitter, there's like a video of AI produced video. It's supposed to be like a cat lying in bed with a person, and the cat will like spontaneously produce like a fifth arm, or like the person will change into a different person when they roll over. And yeah, it's just, there is this uncanniness, which maybe is uncanny for us because there isn't this object constancy which we expect.
Yeah, there was, I think it was Stable Diffusion that, like, for the longest time would produce hands with like the wrong number of fingers. I think they might have like fixed that by now, but there was like, the drift out pulp picture with like, but if you look closely, like he has like 8 fingers or whatever. But yeah, so I think there are like a variety of different types of systems, that like some of the ones that are just like free things you can use online, or like a relatively cheap system. Of course, the outputs are not that great, but there are, the ones that like, Hollywood movie studios are using to like de-age these actors so that we can have like a million Harrison Ford movies where he looks like he did in the 70s. Like, yeah, these are obviously much more sophisticated, and you only see the output after like many, like all the sort of tuning that goes into that process. You only see like the final result, and not like the many steps that were required to get to that result. But yeah, so these are obviously getting much more sophisticated than what I'm sure if you had asked Ruyer in 1965 or whatever, will there ever be like an electronic machine that can take a text prompt and produce a video that is more or less realistic, that matches it? He would have said no. Whereas that is actually not that. I mean, it's not super successful yet, but there are systems that can do something along those lines, and they'll surely get better and better in the next few years. So yeah, it's maybe not quite as like straightforward a distinction between like the grasp of the schema that the human has compared to the sort of processing that this computer can do. Maybe not, the line is maybe not as clear as it would have been in 1965, but yeah, so it's a question now of like whether this blurring of the line is just like a superficial similarity, or does it indicate a more sort of fundamental underlying connection between what the computer is doing and what the human being is doing. One interesting bit actually in connection with this, I forget exactly what it was, but I remember I was at a talk not that long ago where they're talking about analyzing audio inputs, like I think it was speech or something like that. But the way they were doing it was like not actually sort of directly analyzing the audio, but turning the audio into a spectrogram. So this is like an analysis of the distribution of energy across different frequencies in the sound wave, and then doing like visual processing on the spectrogram. So this is like sort of a means of taking a temporal input and turning it into a static visual, sort of as like a pre-processing step. You turn it into the static visual depiction, and then use that to do your processing on. And yeah, so this is maybe like an indication that like the kinds of artificial intelligence or machine learning systems that we are producing now are still sort of operating in this more static way compared to yeah, the schematic or dynamic grasp that humans have. Yeah, so maybe we can end here for now, since it's getting late for those of us in other time zones, and we're almost at our 2-hour mark. So yeah, let's pick up next week from page 35, and yeah, we'll keep going from there. Okay, so thanks everyone. Thanks for the discussion and contributions. Yeah, and see you.